Right now, every server running Linux, every cloud instance, every Kubernetes cluster, every Ubuntu workstation, every Debian production environment, every RHEL enterprise deployment, every Fedora developer machine sitting in a home office is running on top of a 9-year-old security flaw that nobody caught, nobody fixed, and that any attacker with a basic shell account can exploit with a script shorter than a text message. This is not a theoretical vulnerability being discussed in an academic paper. This is not a proof of concept that requires nation-state resources to weaponize. This is a publicly disclosed, actively exploited, fully documented kernel flaw with working exploit code sitting on GitHub right now, available to anyone who wants to use it, capable of turning any unprivileged local user into a full root administrator in seconds, leaving absolutely no trace on disk, vanishing completely on reboot, as if the attack never happened. The Linux security community has spent decades building a reputation on the idea that open source code means more eyes, more scrutiny, and fewer dangerous secrets. That reputation just took the hardest hit it has ever received, and the damage is spread across not one vulnerability, but 4 separate 9-year-old flaws disclosed within a single month in 2026. The kernel was broken the entire time. The world just did not know it yet. The vulnerability that has generated the most immediate alarm is officially tracked as CVE 2026-46333 and has been given the operational codename SSH keysign Pyelon by the Qualys Threat Research Unit, the team that discovered and responsibly disclosed it. The flaw lives inside the Linux kernel's item-backed trace may access function, a piece of code that governs whether one process is permitted to inspect, trace, or interact with another running process on the same system. This function has existed in essentially its current broken form since Linux kernel version 4.10 RC1, which was introduced in November 2016. For 9 years, this function has contained a logic error so subtle that thousands of kernel developers reviewing the codebase never identified it. The error creates a brief but exploitable timing window during which a privileged process that is in the middle of dropping its elevated credentials, transitioning from a high privilege state to a lower privilege state in the normal course of its operation, can still be accessed and traced by an unprivileged user. That window should be closed. The kernel should prevent access during that transition. It does not. And that failure of a few lines of logic has created a path from any basic shell account straight to full root access on virtually every major Linux distribution that has shipped since late 2016. The practical consequences of CVE 2026-46333 extend far beyond simple privilege escalation. Qualys researchers demonstrated that by exploiting the timing window in Nijawar ptrace may access and combining it with the PIDFD system call, a legitimate kernel feature that allows a process to obtain a copy of a file descriptor belonging to another process, an attacker can reach into the memory space of privileged processes and extract open file descriptors that should be completely inaccessible to unprivileged users. In practice, this means that the attack can steal SSH private keys directly from the memory of SSH keysign processes running on the affected system. SSH private keys are not just passwords. They are cryptographic credentials that grant authenticated access to every other system that trusts the compromised key. An attacker who steals an SSH private key from one compromised system does not stop at that system. They use the stolen key to move laterally across every other server in the infrastructure that was configured to trust it, which in enterprise environments, cloud deployment, and development pipelines can mean hundreds or thousands of machines falling like dominoes from a single initial exploitation event. Qualys was explicit in its disclosure guidance, stating that on any host where untrusted local users may have had access during the 9-year exposure window, administrators should treat all SSH host keys and locally cached credentials as potentially stolen and rotate them immediately. The proof of concept exploit for CVE 2026-46333 was released publicly within days of the vulnerability's disclosure, and security researchers who reviewed it described the exploit as reliable, deterministic, and straightforward to execute. There is no probabilistic component. There is no requirement for specific kernel debugging features to be enabled. There is no dependency on unusual system configurations or pre-installed attack primitives. Any system running a vulnerable kernel version, which is essentially any Linux system running an unpatched kernel from the last 9 years, is exploitable by any user who can obtain local shell access, whether that access was obtained through a compromised developer account, a misconfigured service, a supply chain breach, or any of the dozens of other initial access vectors that attackers use to get their first foothold inside a target environment. The primitive, as Qualys described it, is reliable and turns any local shell into a path to root or to sensitive credential material. That is not security research hyperbole. That is a factual description of what the exploit does, consistently every time it is run. CVE 2026-4633 alone would be the most significant Linux kernel security disclosure of 2026, but it did not arrive alone. In the 30 days before its disclosure, the Linux kernel security community was already reeling from 3 other 9-year-old vulnerabilities that had been discovered and published in rapid succession: copyfail, dirty frag, and fragnesia. The fact that 4 separate critical kernel vulnerabilities, all dating back to 2016 or 2017, were discovered and disclosed within a single month is not a coincidence driven by random chance. It reflects a structural shift in how security research is being conducted. AI-powered code auditing tools are now capable of scanning millions of lines of kernel source code at speeds and depths that human reviewers cannot match, identifying subtle logic errors in functions that have been reviewed and approved by skilled engineers and still slipped through. The Qualys team, the Theory Shant code research team, independent researcher Hyunwoo Kim, and others are all using these tools to go back through decades of kernel code and find the vulnerabilities that human eyes missed the first time, the second time, and every time since. The result is a disclosure pipeline that is accelerating, not slowing down, and the Linux kernel is the primary target. Copyfail, officially tracked as CVE 2026-31431, with a CVSS severity score of 7.8 and classified as high severity, was discovered by the Sint code research team at Offensive. Security research firm Theory, using an AI-powered auditing tool following an initial lead from researcher Taiyang Li. The flaw is rooted in a logic error inside the Linux kernel's cryptographic subsystem, specifically within the Aljif AED module that handles authenticated encryption operations. An optimization introduced in 2017 intended to speed up data encryption by improving how the kernel handles page cache operations inadvertently blurred a critical safety boundary between read-only file data and writable memory during cryptographic processing. The result is a vulnerability that allows any unprivileged local user to trigger a deterministic, controlled 4-byte write into the page cache of any readable file on the system, meaning they can modify the in-memory representation of files they should only be able to read, not write. By targeting a set-to-it binary, an executable that runs with elevated privileges when called, the attacker can modify that binary in memory and use it as a stepping stone to full root access. Theory's public proof-of-concept exploit runs in 10 lines of Python. It works 100% of the time. It leaves no modification on disk. The entire attack happens in temporary memory and disappears, completely on reboot. CySA added CVE 2026-31431 to its known exploited vulnerabilities catalog within 24 hours of public disclosure, citing evidence of active exploitation in the wild, meaning real attackers were already using this flaw against real systems before most administrators even knew it existed. The confirmed exploitation targets for copyfail include Ubuntu 24.04, LTS, Amazon Linux 2023, Red Hat Enterprise Linux 10.1, and SUSE 16, between them representing an enormous fraction of all enterprise Linux deployments on Earth. Every organization running workloads on AWS using Amazon Linux 2023 was vulnerable. Every enterprise running RHEL across their server infrastructure was vulnerable. Every developer running Ubuntu 24.04 as their primary workstation was vulnerable. Because the exploit requires only an unprivileged local use, R account and no network access, no kernel debugging features, and no special pre-installed attack primitives, the attack surface is defined by any context where an attacker can obtain any form of local shell access, and in the modern infrastructure landscape of shared developer environments, CI/CD runners, multi-tenant Kubernetes clusters, and cloud instances with multiple users, that context is extraordinarily common. Dirty Frag, disclosed approximately 2 weeks after copyfail, introduced a third generation of kernel vulnerabilities in the page cache write family that copyfail had already exposed. The flaw was discovered by independent security researcher Hyunwoo Kim, who identified 2 separate vulnerabilities: CVE 2026-43284, which targets the IPsec XFRM ESP path, and CVE 2026-43500, which targets the RxRPC protocol, and demonstrated that chaining them together creates a reliable route escalation path that covers the blind spots of each individual flaw. CVE 2026-43284 normally requires namespace permissions that some distributions like Ubuntu can block. CVE 2026-43500 does not require special permissions, but depends on the RxRPC module being loaded, which is not universal. By combining both, Kim showed that the attack covers scenarios where either individual vulnerability would be blocked, creating a chain that achieves reliable row T-access across a broader range of Linux configurations than either flaw could reach independently. Kim originally planned to hold the technical details until fixes were ready, but moved up the disclosure timeline, after observing that the copy fail disclosure had already put the research community and threat actors on notice that the page cache write class of vulnerabilities was a productive attack surface. The fourth vulnerability in this extraordinary 30-day sequence, Fragnesia, targets network packet fragmentation handling in the kernel and follows a similar pattern. A subtle logic error introduced years ago in code that has been reviewed repeatedly without the flaw being identified, now discovered by a researcher using systematic automated analysis rather than traditional manual code review. The details of Fragnesia are less fully public than the other 3 vulnerabilities at this writing, but its inclusion in the same disclosure window reinforces the broader pattern that is now unmistakable. This is not a run of bad luck. This is what happens when AI-assisted code auditing tools are pointed at a code base that has grown to tens of millions of lines of code over decades, where the original authors of specific functions may no longer be active contributors, where the interaction between different kernel subsystems creates emergent vulnerability conditions that no single reviewer would identify while reviewing any single component in isolation. The implications for cloud infrastructure are what make this moment genuinely alarming beyond the typical cadence of kernel CVE disclosures. In a shared cloud environment, a local privilege escalation vulnerability is not contained by the boundaries of a single virtual machine. Container escape scenarios, where an attacker breaks out of an isolated container and reaches the underlying host, are among the most feared attack chains in cloud security. And local privilege escalation in the host kernel is frequently the critical stepping stone that makes container escapes possible. The Kubernetes clusters that run the modern internet are full of containers sharing host kernels. The CI/CD pipelines that build and deploy software for millions of organizations run user-supplied code in environments that share kernel access. The multi-tenant cloud instances where developers work, test, and deploy applications are inherently environments where untrusted local users exist by design. All of those environments were vulnerable to at least one, and in many cases, multiple of the 4 vulnerabilities disclosed this month, and some of them were exposed for the full 9 years that the flaws existed without detection. The remediation path for each of these vulnerabilities is clear in principle, but challenging in practice at the scale of modern infrastructure. For CVE 2026-46333, the immediate steps recommended by Qualys are to apply the latest kernel update released by Linux distributions, raise kernel.yama.pttrace, scoped to 2 as a temporary workaround on systems that cannot be patched immediately, with the acknowledged trade-off that this setting may disrupt debugging tools like GDB and Strace, and to rotate SSH host keys and all administrative credentials on any system where untrusted users may have had access during the exposure window. For copy fail CVE 2026-31431, the fix is to update to the patched kernel commit, and for systems that cannot be immediately updated, to disable the aljif aid module, which blocks the specific exploitation path without affecting common applications, including web browsers and SSH. These are not complicated instructions. The challenge is that in an enterprise environment running thousands of Linux instances across multiple cloud providers, on-premises data centers, edge devices, and developer workstations, executing these remediations simultaneously, verifying completion, and auditing for signs of prior exploitation before the patches were applied is a massive operational undertaking that takes weeks, not hours. What the 2026 Linux vulnerability wave ultimately exposes is something more fundamental than any individual CVE. It exposes the gap between the theoretical security advantages of open source code, transparency, peer review, community scrutiny, and the practical reality of maintaining a kernel code base that has grown so large and so complex that even the combined attention of thousands of skilled engineers reviewing it continuously over decades cannot guarantee that subtle logic errors introduced in 2016 or 2017 will be caught before they spend 9 years embedded in billions of production systems. The Linux kernel is not broken in the sense that it cannot be fixed. The patches exist. The fixes work. The developers who maintain the kernel responded with speed and transparency that reflects genuine commitment to security. But the kernel was broken in the sense that it contained critical vulnerabilities that nobody found for 9 years, that real attackers are now actively exploiting, and that required AI-powered automated analysis to surface after human review had missed them repeatedly. That is a fact about the state of software security in 2026 that has implications far beyond Linux. It applies to every large code base that has ever been declared secure on the basis of review processes that were designed for a world before automated deep analysis was possible. The question every organization running Linux should be asking right now is not only whether they have patched these 4 vulnerabilities, It is how many more like them are still waiting to be found.